Welcome to this video. So in this video we will talk about what actually is sound and how does sound actually happen on the physical side, on the physics side of it. So one thing you have to know first, that if there would not be little molecules, let me try that again. Welcome to this video. So in this video we will talk about what actually is sound. So when I do a clap, what is really happening? How can I hear this clap in my ears? So one thing you have to know, that in the air there is little pieces, little molecules which make up the air basically. So if there would not be these molecules in the air, there would also be no sound. So if you would have a vacuum, you cannot have any sound. So there's no sound in vacuum. So the air molecules have a strong influence in how we experience sound, in how we hear sound. So let me do a little drawing of you. So I want to explain to you now what actually happens when I clap my hands. So as I told you already, there is this little, lots of these little air molecules in the air. I just try to draw a few of them. And what happens when you clap your hands is basically these air molecules, they get pressed together. So at the moment when my hands touch each other, these air molecules get pressed together. So there is an air, like a contraction of air, like the air pressure at that point where my hands touch each other becomes higher. So there is much more air molecules at one point in space, at the point in space where my hands touch each other. So what happens? The pressure increases at that point where my hands touch each other, and then this pressure is released again. So the molecules get contracted and then they release again and push out to all sides. So what they do is they move back basically, and they push the surrounding air molecules further through space. So these air molecules get pushed, and what is happening basically, there is occurring another increased point in air pressure. So there will be another point where the air pressure increases, where we have a contraction of air molecules, because you have to imagine, at the point where my hands touch each other, the air pressure is high. So it releases and pushes basically into the surrounding air molecules. So it pushes into the surrounding air molecules, and at a new point in space, air molecules get contracted. So we have a new location in space where we have an increased pressure level of air molecules. So at some new point we get again a zone, like a high air pressure zone. So basically the same thing as we had at the point where my hands touch each other. And then the same thing starts all over again. We have this zone where there is higher air pressure, it releases again, pushes the air molecules further through space, pushes the surrounding air molecules, and then a third contraction happens. So they bump into each other, and we have another zone of higher pressure, of more air molecules at one point in space. So that's what's basically happening, and this then goes on through the space, kind of in waves. So this just happens all over again until it reaches basically our ear. So let me quickly draw a human, and it reaches our ear. So let me draw that ear, and there is a little drum, what's it called, drum field, I guess, in our ear. Let me quickly get the correct word for it. Yeah, the eardrum, exactly. So oh, what happened now? Here we go. So it reaches our ear. It reaches our eardrum, and basically our eardrum then starts to resonate with the same rhythm these contracted air molecule waves reach our ear. So the first wave hits our ear, so it starts to bounce in one time, the eardrum. Then the second wave of air molecules contractions basically hits our ear, and then the eardrum starts to go in and out again. And this is how it starts. Basically, the eardrum starts to bounce back and forth. And the eardrum is connected to many nerve endings, which send the rhythm of these waves approaching to our brain. And this is, in the end, how we can hear sound. So the this image on the following slide here basically tries to depict this. So we have some source of sound. We have air molecules which get contracted and push each other forward until they reach the ear. So there's always high pressure zones, low pressure zones in the air, and these waves of air basically hit our ear. And one thing we have to understand here is that this thing, like these air waves, they travel through the air at a certain speed. And this speed is different for different materials. So we can not only have sound in air, but we can also have sound in, let's say, water or iron, steel, or in glass. So when we talk about air, we have to know that the sound, or these air waves, basically they travel through the air at a speed of 342 meters per second. So when I clap and you stand away for 342 meters, it takes 1 second until you can hear my clap. It's pretty different in water. In water, the speed is much higher. It's 1,440 meters per second. So if you would do the same clap, I mean, in general, in theory, if possible, in water, if you just stand 342 meters away, it would take much less than a second until it reaches your ear. Especially in iron and steel, it's really fast. Also in glass, it's over 5K meters per second. Maybe you have tried this once, to put your ear on the rails where a train travels over. Maybe you have realized that you can hear the train when you put your ears on the rails much earlier than you can hear it like when you just stand by the rail and listen to the sound coming from the train through the air. And this is exactly this effect, that the sound which the train puts on the rails is much faster going through the rails approaching you than it goes through the air approaching your ear. So that's at that effect we can basically see these different speeds in sound. So this was the first part. Thank you for watching, and see you in the next video.